Okay, so you're comfortable graphing a linear equation. You've gotten used to graphing the quadratic. But what about when we have a cubic or higher? Stay tuned to find out. Okay, so far you've had nice looking linear equations. You've done your quadratics, right? Which are your polynomials to the second degree. But once they get higher, some weird things can happen. So I can have my graph actually cross the x-axis. Okay, I can actually bring it back down. Notice that it crosses again. Now notice that it doesn't have to cross every time, because I can come up here and I can just boop, just touch and turn around where it, instead of crossing the x-axis. So several different things can happen here. So we're going to take advantage of some advanced techniques so we can make a sketch of what our graphs can look like. Okay, so what we'll actually do is take advantage of our x-intercepts so that we can go ahead and start making our sketch. So I don't know, I'm just going to make one up here. Let's say that we have, I don't know, f of x is equal to, I don't know, x minus 1 squared times x plus 2, right? If this is what we have, then to get x-intercepts, just like you've done before, you need to know when these would be equal to 0, okay? So this lets us know that either this x minus 1 squared is equal to 0, or x plus 2 is equal to 0. Now remember, why am I splitting this? Because these are multiplying. It only matters if one of them is equal to 0 for the whole thing to be 0, because 0 times anything here was going to be equal to 0. Okay, and vice versa. If this is equal to 0, then it doesn't matter what we get here. Multiplying, everything's going to be equal to 0. So if I solve this, okay, I'll do it down here, x minus 1 squared is equal to 0. Okay, we've worked those before. Taking the square root gives me x minus 1 equal to 0. And then I get x, adding 1 to both sides, I get x is equal to 1. That is one of my zeros here. And I'll do the same on the other side. X plus 2 is equal to 0. Subtracting 2 on both sides gives me x is equal to negative 2. So these are both scenarios where it would be equal to 0, okay, for this function. Okay? Knowing that, it's known as the zeros of my function, okay, or the root of my function. You'll hear your teacher say those two words interchangeably, okay? It's the same thing. So these are my roots, or these are my zeros, all right? If that's the case, well, we know that this is where I'm going to have x-intercepts. So these, okay, in this case, I was calling them my roots, okay, my r's, okay? Then my roots, then these are my x-intercepts, then my r is an x-intercept, and it's a factor of my polynomial. Okay, so I can say x minus r is a factor. Notice that to make this sketch, we already gave you something that was factored already. Okay, we didn't write it out, you know, expanded already. It was already factored. Okay, like that we'll be able to make our sketches quicker. Okay, so you'll see that better with an example. So here, let's take a look at this problem. This says, find a polynomial of degree 3 whose zeros are negative 3, 2, and 5. So that definition I wrote before, all it's saying is, well, okay, so I have some polynomial, I don't know, f of x, so that these are my roots, okay? So to write them down, all I have to say is, okay, well, I have an x, or whatever variable you decide to use here. I know that before it told me that it was x minus r, right? So I have to say x minus, okay, and what's the 0 here? negative 3. My next 0 is 2, so x minus 2. And my last one is x minus r. So I'm just substituting my zeros inside that r. And notice that I left a little blank spot here. I'll get to that in a second. So simplifying this, I just get x plus 3 times x minus 2 times x minus 5. Okay, notice that if I try to look for my zeros like I did before, I would have to split this up, right? I would say either this is equal to 0, this is equal to 0, or this one's equal to 0. And I would get these answers back. Notice that here, either x plus 3 is equal to 0. Subtracting that gives me x is equal to negative 3, which is what I had before. Okay, you'll see the same thing happen here, which will give me x is equal to 2, and the last one, x is equal to 5. Okay, now I told you I left this spot blank because I can have any number here that I want. Right now I'm gonna, let's say, make an a for any number that I want. And it will not change this. Notice that if I have a number all the way in the front, let's say this was a number 2, does it affect my answers here? No, it doesn't. My zeros stay exactly the same. As a matter of fact, let's go ahead and take a look at this on Desmos so you can see how that can be manipulated. Okay, so here I am in Desmos.com, and I want to prove to you that that coefficient in the very front, that a, doesn't matter what it is. So I'm going to go ahead and click on Start Graphing, and let's put in what we had. So we had f of x is equal to, right now I'm going to leave the a, and our answer was x plus 3 times x minus 2 times x minus 5. Okay, I'm going to add this sliders because that'll let me change the coefficient on the spot. So here, right now, my a is equal to 1. So let me zoom out so you can see what the graph looks like a little bit better. Maybe one more. Okay, so there it is. We have our cubic function here where my a right now is equal to 1. Now what happens, before I do that, let me show you my zeros. My zeros, right, are where it crosses the x-axis are at negative 3, at 2, and at 5, just as we predicted. Now what happens if I increase my a? Let's do this kind of slowly. Notice, wow, it's stretching, isn't it? But what is not stretching are my x-intercepts. They're still at negative 3, 2, and 5. So no matter how big I make this, how much it's stretching out, well, that might be stretched, zoomed out a little bit too much, but no matter what, my x-intercepts stay exactly the same. Now, what would happen, and I'm going to put this back at 1, now what's going to happen if I make that a negative, right? Because that's another thing that can happen. If I make that a negative, wait a minute, notice that I have a reflection about the x-axis. So here I'll just leave it at negative 1. So here, my x-intercepts, they must have changed. Oh, no, they didn't. Okay, my x-intercepts are staying exactly the same. So that's why I was saying that that coefficient in the very front, that a, won't matter. Okay? Now, I think it's your turn to try one out. Go ahead and try this problem, and I'll show you the answers in 3, 2, 1. Okay, so here's your final answer. I decided to use H, W, and B. Do I have to use F, X, and A? No, I don't. Okay, so I wanted to use these so that if case you see different variables, it doesn't throw you off, okay? Just don't get comfortable only using x's. So here your final answer is h of w is equal to b times x plus 5 times w plus 1 times w minus 2 and times w minus 3, okay? Let's go ahead and keep going. Something else I want to point out in this problem is that I limited the degree that we had. I told you that this was going to be a degree 4, and I gave you 4 of the zeros, but that's not always the case. Okay, so let's go ahead and try this one out. We have g of x is equal to x squared times x minus 2, and we're asked to do 3 things. First, find the y-intercept, then x-intercept, then create a sketch of the graph. So, starting off with part A. So for your y-intercept, remember that is where your x's are equal to 0. So we'll set this up as g of 0 equal to 0 squared times 0 minus 2. So easy peasy, lemon squeezy, that gives me 0. Okay? So I know that my y-intercept is where it's at. When my x was 0, my g of 0 was also 0. So we know that our y-intercept is at 0, 0. Let's look for our x-intercepts. Okay, our x-intercepts, well, that's when g of x is equal to 0. So we know that we need this. X squared times x minus 2, when is that equal to 0? Well, once again, that's our scenario. That's why I gave it to you factored. Because either this is equal to 0 or this is equal to 0. Okay? So solving this, square root on both sides, my x is equal to 0, and here adding 2 to both sides, my x is equal to 2. So I have 2 x-intercepts. Okay? I have 0, 0. Okay, so because remember, we're essentially making the y equal to 0. And here, my x is equal, when my x is equal to 2, I also get 0. So my other x-intercept is 2, 0. Huh. Interesting. Notice that this is a third degree polynomial. So traditionally, you might have thought that, well, I should cross the x-axis 3 times, but I only have 2 x-intercepts. So let's see why that is. Okay, so we're going to make our sketch now, and here I just made, a quick graph. So I know I have my x-intercepts at 0, 0. So I have 0, 0, and we'll stretch it out here. Let's say that here's 1, so here's 2, here is my 2, 0. So what this is kind of doing is, well, splitting my whole coordinate plane into 3 different sections. I need to see what's happening with this graph left of my x-intercept and between the 2 x-intercepts and to the right of my last x-intercept. So let's plot a point and see what's happening here. So if I choose any number here, okay, I need an x that's less than 0. So let me just choose -1. So if I substitute in here -1, let's see what's happening. -1 squared times -1 minus 2. Okay, so -1 squared is 1 times -1 minus 2 is -3. And multiplying this gives me -3. So I know that when my x's are here, my y's are negative. So I'll use that point I just made, so -1. So this should be here. -1, -3. So -3. What this lets me know is that somewhere here, remember this is a sketch, that's why I underlined it. Somewhere here I am increasing, I am going up. Okay? Well, what else? I need to choose a point here as well. Remember, I'm trying to look for something that it'll either be positive or it's going to be negative. Okay? So that'll be interesting. So let's see what happens. Choosing a number between, let's just choose positive 1 this time. So I'll do it here. Hopefully I've run out of room. So g of positive 1, well, that gives me 1 squared times 1 minus 2. 1 squared is 1 times 1 minus 2 is negative 1. This gives me negative 1. So that lets me know that in this region, my answers are still negative. But notice that if I just go like this, well, what's going to happen here? Aren't I supposed to come towards this point, toward this x-intercept? So the only way that can happen is if, and remember, it's just a sketch, is if, well, let me point this, graph this one first. So negative 1 would be right around here. Is if somewhere here in this region, I don't know if it's here, okay, just because I made a point to this one, because this one is a coordinate doesn't mean that it turns here, but somewhere in this region, this graph will come back up. That's the only way that it'll reach this x-coordinate. I know, looks kind of weird, but I'll show it to you on Desmos as well so you can see that I'm not making it up. Here, now I need to test this region because what can happen, it'll either cross it or it'll come back down. So let's see. Let's choose a point that's to the right of the x-intercept. So let's say that, let's just 3. So g of 3 is equal to 3 squared times 3 minus 2. So that's 9 times 1 is equal to 9. So I get a positive answer here. I know that 3, 9, okay, so somewhere all the way up here is where my graph goes. So this lets me know that I don't come back down. I am going to cross it and keep going somewhere this way. So you've seen two things that can happen for your x-intercepts. They will either touch it, okay, and go back towards being positive or negative. So they'll either touch the x-intercept or you can cross it. There must be a way to know, though. Haha. There is a shorter way to know whether it's going to turn or cross before you even start to graph things. So here we're talking about multiplicity. Okay, so what is multiplicity? It is the power, okay, the exponent that your root is in. So in this case, my root here is an even multiplicity. Okay, so what did we get here? Well, remember this was when our x was equal to 0. That was this answer right here, our x-intercept when x was equal to 0. This is the one we got. So when our multiplicity is even, then here we know that it will only touch the x-intercept. It's not going to cross it. It's going to do kind of like a U-turn. Okay, it'll touch it and go back where it came from. Now here, okay, when we solve this one, notice that the multiplicity here is 1. Okay, so that's the power I have for this root. So this lets me know that it's even, and whatever answer I get there, which was 2, 0, so that was this one here, it's going to cross. Whoops, wrote it in red. I like to be coordinated, but you know. So here, when it's an odd multiplicity, it will cross that x-intercept. If it's an even multiplicity, it will touch and go back. So you have your U-turn and crossing. Okay, so like that, you'll know whether what's happening there before even trying out the points. Just some quick notes before we move on. So here at my turning points, okay, So like in algebra, we just usually call them the turning points. I know that when you get further on though, you'll look into local maxima and local minima. Okay, so there you can isolate and you'll use calculus to figure out exactly where they are. But here, remember, we're just making sketches. Another question they can ask you is, hey, given, this polynomial, what's the maximum number of times that it can turn? Well, there's a theorem that says that any degree polynomial, okay, so let's say it's degree of n, the amount of turns, that's not how you spell turn, the amount of turns, so the max turns, can be x minus 1. So here we had a third degree polynomial. The maximum amount of turns is, well, 3 minus 1 is 2. So it can turn at most 2 times. It cannot turn more than that. So even if they ask you, oh, I have a 99 degree polynomial, how many times could it turn? Well, the maximum for a 99th degree polynomial would be 98. Okay? Okay, so I did promise you that I was going to graph this one on Desmos, so you can see I wasn't a filthy, filthy liar, right? So let's go ahead and graph this on Desmos. X minus 2. Okay, so we'll have to zoom in here. So take a look at, hey, that looks like our sketch, doesn't it? We have 0, 0. That's what we had. And we had 2, 0. Okay, so we were able to sketch this. Remember, this was broken down into 3 regions. Okay, the left side, the middle, and the right side. And we were able to sketch this. And I did tell you that this does turn at some point. So right now in algebra, we weren't finding that exact number, but with a graphing calculator, we can. Here we see that, oh, it's not 1, okay, like you might have thought. We just know that it's somewhere in this region that it will turn to go back and cross here at 2, 0. Now, you might have noticed something before I even said it. This graph, which is a third degree polynomial, well, it kind of looks like our parent function, y is equal to x to the third. Okay, so I erased the graphs before I was able to say this next part, but don't worry, magic of editing. So here in blue, we have the graph that we sketched together, and in red, we have our parent function, f of x is equal to x to the third power. Now, you'll notice that, yeah, here towards the middle, they look different, but as we go further and further along, they start to look almost the same. Okay, so the way that we call this, their end behavior is very similar. They're going to behave in the same way. So let's take a look at the ending behavior that will also help you graph. Okay, so let's take a look at what can happen here. If the degree of my polynomial is an even number, okay, so it has to be greater than or equal to 2, and it has to be even. So no matter what it looks like, if my degree of my polynomial is like this, well, let's take a look at the parent function first. This matches the end behavior of our quadratic. So if our coefficient here is positive, so let's say that a is positive, I know that a quadratic looks like this, right? My parent function for the quadratic looks just like this. Now, I don't care about what's happening in the middle, because crazy things can happen in between, but at the end, remember, this is my end behavior. I know that no matter what, my end behavior will look something like this. My graph will decrease in the very beginning, but it will end up increasing as x approaches infinity. So I'm only looking at my ending behavior, the beginning and on to the right. Okay, so what happens if my a is negative? Well, if my a is negative, well, remember my quadratic, my parent function looks like this, right? We have a reflection about the x-axis. So looking at the ending behavior for this, remember, that means I only care about what's happening right here. Well, I know that my graphs of all even functions, okay, so even if they're doing all these crazy things all the way up here, the ending behavior will always be exactly the same. So here as x approaches negative infinity, I am decreasing in value, and likewise here as I approach positive infinity, I'm also decreasing in value. So even if my graph does crazy things, I don't know, it does all this craziness, my end behavior will look like this, okay? It's probably too crazy, but ending behavior is the same. So here, likewise for my end behavior, and we kind of saw it earlier, is if my polynomial has a degree of 3 higher and it's odd, the end behavior for that correlates to our parent function of the cubic. So if my a is positive, remember our cubic function looks like this. So you look at the ending behavior, what's happening here, and we know that no matter what, my ending behavior looks like this. And likewise, if my a is negative, well, we have our reflection about the x-axis again, and we have, well, I have to stay color coordinated, and we have this. So we know our ending behavior for all those polynomial functions looks like this. Okay, let me prove it to you with that power of Desmos. Okay, so let's take a look at comparing the power function to what we just looked at, right? Because we're just looking at the end behavior. So here in red is my power function, and blue is the one that I'm going to manipulate. And you'll notice that right now my blue and red are exactly the same. Well, that's because if you notice what I have, my power function or parent is x squared, right? And here I have a, which right now I'm saying is equal to 1, and I have x times x. So x times x is x squared, so that's why they're exactly the same. But we said that all of the even ones should have a similar end behavior to our power function. So let's take a look at what happens if I take this to the fourth power. So if I take this to the fourth power, then yes, I don't have my quadratic anymore, but my end behavior is still the same. It's still decreasing on the left side and increasing on the right. Or you might be using some more advanced notation and saying as x heads towards negative infinity. Okay, so you're comparing it from the origin. So as x approaches negative infinity, my y's increase, and as x approaches positive infinity, my y's increase as well. So, and you hear some teachers say that this is like up and up. Okay, but let's play around in here and see what happens when we start to mess around with things. Let's do +3 and a -4. Okay, well, let's zoom out from here. Okay, so let me look at just the blue one, and it looks like a W, right? So here I have a 4th degree polynomial, and look at my x-intercepts. We should be able to pick them out really quickly from what I added here, but notice at the end behavior, okay, so it's doing all these crazy turns here, but it doesn't matter because my end behavior, notice that it's still the same as before, decreasing on the left, increasing on the right, just like I have here for my parabola. Okay, so just looking at the ends, it gives me the exact same thing. And just like before, what happens if I have, I don't know, a negative a? So in this case, let's make this into a negative a. I gotta fix this. So if I make this into a negative a, whoa, I have my reflection of the x-axis, right? And I know it's harder to see here, but my end behavior is still the same. Okay, so this time I am increasing on the left side, decreasing on the right. And no matter the crazy things that happen, in between, my end behavior is going to match up. I don't know, +3. Okay, so I have my w, but all I care about is the end behavior, it still matches up. Let's look at the odd functions now. All right, now this time I have the parent function for the cubic, right? So I have it to a third power. I'm just showing you that, you know, the rules still apply. They're still exactly the same for the end behavior. So here I have 3x's multiplying, so that still gives me x to the third. I have my a set to 1, so I know that it's positive. So let me look at my blue, and yeah, look, it matches up exactly what I had for my red. Right now they're exactly the same. But what happens when I start to mess around with what's in here? Once again, let's do +1, -2, and then 3. Okay, so I have, you know, a crazier wave that's happening here. But if I zoom out, I can see that my end behavior is still acting the same way. That's why I was saying the middle parts is where you'll have a lot of difference for your sketches, but the ending will be the same. So increasing on the left, increasing on the right, or if you're using the approach notation, then you're saying as x approaches negative infinity, my y's are decreasing. As x approaches positive infinity, then my x's are increasing. So even if I add more in here, so notice that I added 2 more in here, so I can have it to the 5th power. So if I have this to the 5th power, let's do -4 and +5. Okay, whoa, okay, let's definitely zoom out. A lot of crazy things happening here. Zooming out, zooming out, zooming out. We can't really see what's happening here in the middle. On the right side, we see that it's still increasing, and on the left side is it has the same end behavior, still increasing here on that left side. Okay, and so the exact same thing is going to happen here when we change our a. Let me take this back home and not make this as crazy. And when I have my negative a, it's still the same thing, decreasing on the left, decreasing on the right. Okay, no matter what's happening here in the middle. Okay, so for this problem, this is what I would like you to find out. Okay, so 3 different parts, so it'll be long, so make sure you pause this. A, I want you to find the real zeros and their multiplicity. B, determine if the graph touches or crosses the x-intercepts. And do me a favor, graph that too. We're gonna add that in there so we can make a nice visual. And C, find a power function that matches the end behavior. So let me move out of the way. Go ahead and try this problem, and I'm going to show you the answers in 3, 2, 1. Okay, so here's my answer for just part A. Here I have my real zeros are -3 and 7, but my -3 has a multiplicity of 2. Remember, where did I get that number from? That is our exponent for that factor. And my 7 has a multiplicity of 1 because, same thing, that is my exponent for that factor. Let's look at part B. So in part B, remember that because my multiplicity is even, then I'm at this point at -3, 0, it's only going to touch that x-intercept. But here, because my multiplicity is odd, is going to cross that x-intercept. So what I'll do is that as I'm graphing, I'm also going to be doing C, because I'm going to be thinking about the end behaviors of my graph. So in this case, I have an odd, almost said even, I have an odd degreed polynomial. So this is to the third degree. Remember that this is a 1 right here, and if I'm multiplying this, then my exponents, I need to add them. So this is to the third degree. There's a third degree polynomial. So this matches my cubic power function. So I know that it'll look something like it should. My end behavior is downward on the left, upward on the right. Okay, so I know it should look something like that. By knowing that, that's already helping me graph. I know that, remember, this is going to look something like this, and here it'll look something like, well, I would already know, it looks something like that. Okay, so boom, I have the ending behavior of my graph already made. So, but something happens here. This will either go up and back down, or it's doing this. Well, that's what this was for, our part B. If you remember, we said that at this point, at -3, 0, this had a multiplicity of 2, which is odd. Therefore, this is going to touch and come back down. Okay? And here we said, so this was touch, and here at 7, 0, it was going to cross. So we know that at some point it will go back up again. Okay? Remember, we are sketching here. So for the last thing today, let's just take a look at what this graph actually looks like on Desmos. Now, here I've already written down our function, and when I show it to you, you'll notice that, hey, look, I have my x-intercept here at -3. I have my other x-intercept at 7. In this case, because we had a multiplicity of 2, which is even, we just touched it and came back down, right? That's our U-turn. And here we crossed it because we had a multiplicity that was odd. So I'm going to zoom out so you can see that, remember, we had a sketch, and if you worked out the y-intercept, you would have seen that it was a huge negative number. It was at -189 because you ended up multiplying 3 times -7 times 9, and that gave us -189. But our sketch, the general shape of our sketch, does match the actual graph, where we're showing where it crosses. We're showing that here it's staying in the negative region. It doesn't go positive until it crosses 7. Okay, so I hope you had a good time. Go ahead and try some more problems out from your class, and I'll see you next time.